All right, number 12, a block of mass m is pulled across a rough surface as shown above. I do show it above. Let's get a free body diagram on here. So we're going to end up getting, for our free body diagram, we're going to end up getting, so we got F, we've got the weight, which I'm going to call mg right now on this. This is going to be friction, and we got a normal force, and this is just great. So when we split this into components, we're going to get F cos theta, and another one, F sine theta. So let's set up our equations. We're going to have n plus F sine theta minus mg equals 0. And it's moving at constant speed, so that means things balance. We got F cos theta equals the friction. They balance. So those are our two equations. Now we want to know the frictional force right here. So we need to figure this out. So we know that n equals mg minus F sine theta. So here, the normal force times mu will equal the friction. So I'm getting that the friction force is mu times mg minus F sine theta, which is choice E. And that's number 12. Now for number 13. Wow, so the 500 kilograms for it. Once again, we don't really care about the mass. So the acceleration is going to be 30 divided by 6, which is 5. How did I get that? I got that from v equals at plus v naught and doing it in my head. So again, 30 equals a times 6 plus 0. So that's the acceleration. Then I'm going to use 1/2 at squared, which is 1/2 times 5 times 36. That's going to be 5 times 18, which is 90 meters. And then number 14, an object is moving in a straight line and its speed is increasing at a constant rate. Well, that is the classic example of steady acceleration. That is, acceleration is a constant. And so what that means is the net force is constant but not 0. I didn't say is the speed increasing, I said is the acceleration increasing, and it's not. Now here we've got this box and it slows down to rest. So let's be clear. We need to get the acceleration because here's the deal. I have the normal, I've got the weight, I've got the friction slowing the box down. So we need the fact that friction is mu times n. And so I know that mu is unknown. mg is going to be 200 because that balances the weight, because it's going to be 200 newtons equals weight, which balances the normal. Okay, and so let's get the friction force. Well, I know that the friction is the thing producing the acceleration. And the acceleration, well, I don't have time, so I'm going to use v squared equals 2ax plus v naught squared, that's 0. So what I can say is v squared over 2x equals a. So let's get the acceleration. 10 squared is 100 divided by 2 times 25. So I'm getting an acceleration of 2. So the friction force is going to be 20 times 2, which is 40. So I'm going to get 40 equals mu times 200. And when I actually simplify that out, that is going to end up being B 0.2. Make sure I absolutely get that right. Yeah, I guess so. So the acceleration is 2. 20 times 2 is 40. 40 is mu times, yeah, okay, nice. So now the frictional force was exerted on the box versus floor. This is a total third law question. What we're saying is that there's a friction on the box, and then there's a partner friction on the floor. So it's to the left and to the right. Since the box is moving to the right, the friction acts to the left, and that determines that the friction force on the floor, scuffing it, is to the right. Now for 17, a particle moves in a straight line, so let's be clear. The acceleration is dv dt, which is going to be, when we take the derivative of negative beta, v naught e to the negative bt. Now notice, this expression here is just the same thing as b. So the acceleration is negative beta times v. Students always ask me, how did I know to see that experience? And that is what you were getting on this practice test. So I may put a similar question like that on the real exam. So force, I may not though. Oh, so mean. Okay, so here we go. Let's set up the equations for this box here. Now, to break this down really carefully, we've got big F. We've got the force on the 2 kilogram box due to the 4. And then we've got the normal on the 2 due to the floor. And then we have the weight of the 2 due to the earth. And then for the 4 kilogram, we've got the weight of the 4, or we got the force of the 4 due to the 2. We've got the normal on the 4 because of the floor. And then we have the weight of box 4 kilogram due to the earth. So we can actually set up our equations here. We can actually say that F minus F24 equals 2 times 2. And then for the other box, we have F of 4, 2 equals 4 times 2. It's 4 meters per second squared for the acceleration. So that means F42 equals 4 times 4, which is 16 newtons. And then for number 19, ooh, this is a great question. So first of all, let's actually do number 20 first. How does the magnitude of the force exerted by the ball on the racket compare to the So we have force of ball on racket. How does that compare to force of racket on ball? Whenever you see this phrasing where they shift the subject and the object of the sentence, you know that it's equal because of Newton's third law. Now here though, let's just get this force. So the ball comes in at 15, and you know how you see this arrow says opposite of this arrow, like it points in the opposite direction? That's a clue that this is actually negative 10 meters per second. So I'm going to use v equals at plus v naught to get the acceleration. So I'm going to say negative 10 equals a times 0.03 plus 15. So I'm going to end up getting negative 25 over 0.03 as my acceleration. And then the force is going to equal m times a, which is going to be 0.06 times negative 25 over 0.03, which ends up being actually 2 times negative 25, and that works out to give me a magnitude of 50 newtons. So that wraps up your practice test. I'm going to throw these on YouTube along with the PDF solution, and we should be good to go.